Hello everyone and welcome to St. Andrew's Institute of Technology and Management, Gurgaon, Delhi NCR. St. Andrew's Institute of Technology and Management is the best engineering college in NCR, Northern India and entire India. It is the best choice in terms of education. We provide 100% placements. The subject that I shall be taking is Principles of Operating System. The code is PCC CSE 206G. This is a CSE 4th semester subject. The topic that would be covered are process control block, that is PCB, and context switching. And I shall be Shalini from CSE department. Process control block, PCB. Now what is PCB? A process control block or PCB is a data structure that is used by the computer's operating system to store all the information about a process. Right? Like when a process is created, initialized, or installed, the operating system creates a corresponding PCB. So, whenever there will be a process that will be created, along with it, it will have its own PCB. Information in a PCB is updated during the transition of process states, right? So, when will the PCB get updated? Whenever there will be a process transition state. When the process terminates, this PCB is returned to the pool from which new PCB can be drawn. So, after the termination of the process, the PCB is again returned to the pool from where new PCBs are drawn. Each process has a single PCB, right? See, there is a PID, that is a process ID, and a process control block. So every PCB is going to be assigned a PID, and these, see, every PCB has its own PID to identify itself, right? So how do you know which process has which PCB? So there has to be a naming mechanism now, right? So who helps in identifying it? The PID. Okay. Now, while creating a process, the operating system performs several operations. To identify these processes, it must identify each process. Hence, it assigns a process identification number to each process, and this PID will uniquely identify it. Okay. As the operating system supports multi-programming, it needs to keep track of all the processes, right? For this task, the process control block PCB is used to track the process execution status. So, who executes the PCB execution status is tracked by the PCB. Each block of memory contains information about the process: state, the program counter, the stack pointer, the status of open file, scheduling algorithm, etc. All this information is required and must be saved when a process is switched from one state to another state, right? So whenever you switch state, it has to be updated and also saving the previous one and then going to the next one. When the process made transitions from one state to another, the operating system must update information in the process PCB. So whenever you go from one state to the next state, you have to update the PCB. You have to update the PCB, and it's really required, right? And this is needed for multi-programming. This is very clear, right? Because PCB keeps the state. And why do you need to keep the state? See, if only one process was supposed to be executed, you don't need to keep any state, right? So because there are number of processes, because the multi-programming is going on, so the status has to be kept now. That is why you have this, and this is very helpful. Okay, so what are the various information that is contained by process control block, right? Naming the process, state of the process, resources allocated to the process, memory allocated to the process, scheduling information, input output devices associated with process, right? All these information will be contained in the PCB: the name, the state, the resources, the memory required, the scheduling information, the devices associated with them. Everything about the process will be in PCB. Okay, right. Next we come to structure of the process control block. See, here in this is, we can see this is a process control block. Diagram is here, and we see that it has multiple data items, right? And there are a number of them, see, and the still dots are being continued, and they are all needed for the efficient process management. We see a process state is there, we see a process number is there, we see that there's a program counter. Okay, and then there are registers, there are memory limits, and there are list of open files. And this is going on like any other information about the process, whatever things the process will require, whatever scheduling information, the input output information, whatever it will need, the process control block will have everything, right? And it's a storage structure. See, it's a data structure, right? So that is why it is said to be a data structure. It is all data are being collected over here. So here we look at it one by one, huh? Okay. The first one is the process state. What is the process state? This specifies the process state, that is new, ready, running, waiting, terminated. See, we discussed in the previous lecture, in lecture the previous one, what we studied the various states of a process, if you remember. And they were very stages, like the very when the process was about to being created, it was new. When it was it had all the resources, and it was just waiting for a term to get the CPU. Then it was in ready state, and then there was this running state where the process was going into execution, right? The waiting state, when it was waiting for any input output, or waiting for interrupts, or waiting for any user kind of a defined input or whatever. And then the terminated state, when they were skilled. So all the state of the process, to which state the process was executing when the interrupt came, so this will be contained in the PCB, right? Process number. Okay, the process number, it shows the particular process number that is being assigned to it, right? So it's unique. Okay, the program counter. This program counter, it contains the address of the next instruction that needs to be executed in the process, right? So it will have the next instruction address as to now which instruction is going to be get executed after completing this instruction. That is, if n is the instruction that is being carried out, so this will contain the n plus 1th instruction address. Okay, register. This specifies the register that are used by the process, right? Like which are the register that the process is being using or it will use. So they include like various registers, accumulators you have, index register, the stack pointers, the GPP or the general purpose registers. So all this will be contained inside it. Then there's list of open files. What are open file? These are the different files that are associated with the process. All the files, like suppose if it is reading for some file and it is writing into the other file, then this will contain all the list from which it is reading and the one that it is being writing to, or all the file that it is modifying to. So it can be n. That's why it is written n. That is why it is written list, because they can be multiple also. This is a list of open files. Okay, then there is CPU scheduling information. See, CPU scheduling is a very in-depth topic that has to be covered. It's very important. We will discuss it as we advance into our syllabus. This is the process priority, as to which is the priority of the process, like high priority, or it is medium priority, or it is low priority. So all this information, the pointers to the scheduling queues, Okay, now now it will contain a pointer that will point to the scheduling cues. CPU does scheduling with the help of various cues it has. ठीक? Right? So it will contain all the pointers to the scheduling cues. Okay, and the CPU scheduling information, all the information that is required, like which kind of scheduling it is being employed, and what how it is being done. So everything is being contained in the CPU scheduling information, and there are other parameters also. So everything, like everything about the this will be contained in our PCB. And next we come to memory management information. The memory management information includes the page table or the segment table, depending on the memory system used. It also contains the value of the base registers, right, and the limit registers. The base register and then the index to it gives the actual address. So this will contains everything. It will contain the base address, and it will add on to value it to add to giving you the correct address. The limit registers it will have what is the limit, right, and it will have all the page tables or the segment tables. Everything will be in this memory management information will be contained in PCB. Next is the input output status information. This information includes the list of input output devices used by the process, the list of files, right, and whatever the input it is taking from. Suppose it's a clickable event, then it will wait for an input from the mouse. If it's a keystroke event, that will wait for an input from keyboard. And if it's supposed to write something into the print, it is going to print something, so then it will write, the output will be there, right, for printing. So all this will be contained in the process. Then is accounting information. Accounting means the time limits, the account number, the amount of CPU used, the process numbers, etc. are all part of PCB accounting information, right? So it keeps a track. Next is the location of the process control block. The process control block it kept in a memory area that is protected from the normal user access, and this is very important. Right, this is done because it contains important process information. Some of the OS place PCB at the beginning of the kernel stack for the process as it is safe location. So usually it is kept in the kernel stack, like in majority of the cases, and like to make it fast, it is usually kept in the beginning of the, so that you don't take much time to it, and this has to be kept away from the user. The user should not be able to see as to what exactly. So this is hidden from him, right? Okay, so this was all about PCB. I hope it is clear and you have no doubt in it, right? Next we come to context switching. Okay, what is the process of context switching? A context switching is a process that involves switching of the CPU from one process or task to another, right? In this phenomena, the execution of the process that is present in the running state is suspended by the kernel, and another process that is present in the ready queue is executed by the CPU, right? So it is kind of multitasking, right? Suspending the one that is running and it is taking the other one. So context switching involves storing the context or state of a process so that it can be reloaded when required, and execution can be resumed from the same point as earlier. This is a feature of multitasking operating system, and it allows a single CPU to be shared by multiple processes. You cannot directly switch a process from a running state to a ready state. You have to save the context of that process. If you're not saving the context of any process P, then after some time, when the process P comes in the CPU for execution again, then it will start executing from the starting only, right? So now we see how important it is to keep the state. That is why PCBs are needed. But in reality, no, it should be continued from the point where you left it, right? It should not start from the beginning, right? So the context of the process should be saved before putting any process in the running state, and that's really very important. A context is the contents of a CPU's register and program counters at any point in time. Context switching can happen due to the following reasons. What are the reasons why it occurs? When a process of high priority comes in the ready state. In this case, the execution of the running process should be stopped and the higher priority process should be given the CPU for execution, right? That is why it has a higher priority. Higher priority means that whoever is running, so it needs to be preempted and I'll be the one who's going out and running over there. So that's why it has a higher priority. When an interruption occurs, then the process in the running state should be stopped and the CPU should handle the interrupt before doing something else, right? In case of interrupt handling, so whenever an interrupt occurs, it has to be preempted and then the interrupt has to be handled. Third is when a transition between the user mode and the kernel mode is required, then you have to perform the context switching whenever there is a transaction between user to kernel. And what are the steps involved? So in the figure, if I talk without the steps, if I just see the diagram, there's this process P1 on the top left side and there's this process P2 on the top left side, right side, and there's the CPU. See, now process P1 was executing. You can see the blue arrow down there. Then there's an interrupt that occurs. So what it did, it saved the state of PCB1 and it reloaded from PCB2, and then then process 2 started. So this state it was, and in this process the process P1 becomes idle. Earlier it was process P2, it was idle. Now it is executing. So we see the blue arrow in this process P2. Then what happened, then there's an again interrupt, then again it will save process PCB2 and it will reload from the state PCB1, right? And then this will P2 will be idle and then P1 will start executing. So this is very clear diagram wherein it is showing very clearly how it is being taking place, how it is saving the previous PCB1 state and how it is reloading the PCB2 state. So this is extremely very easy diagram and it is very informative also. See, the diagram depicts the process of context switching between the two processes P1 and P2. So in the figure you can see that initially the process P1 is in running state and process P2 is in ready. See here again, P1 is in executing state and P2 is in the ready queue, right? Now when some interruption occurs, then you have to switch process P1 from running to the ready state after saving the context and process P2 from ready to running state. So how it is performed? See, first is how it is being done. Firstly, the context of P1 that is present in the running state will be saved in the process control PCB1. See here. So save state into PCB1. So that interrupt came. So first the PCB state was saved. Save state into PCB1. Right. Next step. Now you have to move the PCB1 to the relevant queue. That is ready queue, input output queue, waiting queue, etc. So now it will wait. Now third may from the ready state we'll select the new process that is to be executed. This is process P2. See, reload state from PCB2. So the state for running P2 the state is reloaded from PCB2. Whatever, it can start from the initial or it might be executing prior also. See, now you see how it is being run, how it is being written also. And fourth, it says now update the process control block of process P2, that is PCB2, by setting the process state to running. If the process P2 was earlier executed by CPU, then you get to the position of last executed instruction so that you can resume the execution of P2. Similarly, if you want to execute the process P1 again, then you have to follow the same step. See what you did? Now I have to execute P1, then I saved this PCB2 and I reloaded PCB1. And then again I start executing P1. Very easy, na? So for context switching to happen, two processes are at least required, because even in a single process you cannot do context switching. With whom it will switch to? It is alone. So at least two processes are required. In case of round robin scheduling, you can perform context switching with the help of one process, because round robin does like this, na? It has a time quanta that is fixed. We'll study it in our next lectures. The time involved in the context switching of one process by other is called the context switching time, that is CST. We come to the end of it. Now there are some important questions The first one is what is PCB, what is the role of PCB, what is the structure of PCB, what is the need of PCB. See, if it is a combined 10 marks question or something of that, so then all these four are supposed to be combined. The 1 to 4 question are all. So I mentioned it in different sets so that you make it is clear that what is the role of PCB, what is the need of PCB, what role it is performing, why was it needed, and what's the structure of PCB, what is it, right? So it has to be clearly explained with headings and all that stuff. Next is what is context switching and why it is needed, or it can say explain context switching with the help of an example. So in example you're supposed to do the diagram the way I did in by taking one process P1 P2. You can take three processes also, so the diagram has to be big, you need to explain it with that. I hope this lecture was really helpful for you. In case of doubt, please contact. Thank you so much. Have a great day.